think you're muted.
How did I go from muted to unmuted just by hitting record? Oh, well.
Now we can hear you.
Great. I think I mentioned this before, but there's something that's not ideal about the setup of this room, which is that while I am at the board teaching, which I'm going to be doing a fair amount, I can't really see the chat screen. So much better to turn your mic on and interrupt me if you have questions than to type something in the chat, because I'll only get back to it when I go back to my computer, which I'll typically do just to show demos and such. I haven't created the homework assignment turning in part of the homework. I don't know if you guys have read over the syllabus that I posted. If you have, this class is in fact not happening in 2020. It's happening in 2021. And I didn't get any objections about shifting the discussion time, so I'm going to do that. And I'll make both those changes probably while you're doing the lab tonight, because I don't anticipate a lot of student questions during the lab. So I want you to watch me and be alert about mistakes that I make, especially on Tuesday. I teach astronomy until 10 at night, and we always go all the way until 10. And then I'm up at 6 to get to Cal, and I'm not the kind of person that goes to bed easily. Suffice it to say that I am tired. If I'm gonna make mistakes, it's gonna be on Tuesday. And I make mistakes anyway. So be critical of the stuff I write on the board. So I'm gonna start with a quick review of Maxwell's equations, because this is a class about light. I'm gonna say that so many times you're gonna get sick of my hearing it. And the first thing I'm gonna do is I'm gonna dump you guys into discussion rooms after I write some questions on the board. Breakout room, sorry. I want you to discuss what you think the answer is. I'll give you a minute to do it, then I'll pull you back and solicit feedback from the class. This is my poor approximation of the kind of discussions that I do all the time during class. So, in order to see this, when you go into the breakout rooms, you're going to need to do a screen capture. So if you don't know how to do that, use the time that I'm writing out on the board to look it up real quick. Once you do a screen capture, as long as one person in the breakout room has done it, you're going to be able to share that with the other people in the breakout room. But make your own screen capture. These are the 3 questions. The first 2 are a smidge of review. I'm hopeful that everybody will get them, although realistically, not everybody will. The third question is one of the key questions for this class. And I can see that one is a little bit off the screen. And also the screen is a little keyholed. That's not great. Oh well. Get your screen capture. I'll try to straighten the camera while you are in the breakout rooms. If there are still breakout rooms, this new version of Zoom doesn't seem to have them. That is just fabulous. Let me click around to see if they truly are vanished, or if this is still a teaching tool I have available to me. In the meantime, think yourself about what you think the answers to the questions are. Breakout rooms are gone. I never thought I'd miss CompuZoom, but now I do. In the absence of a healthy discussion, does anybody feel like sharing what their answer to problem number 1 is? How do you create an electric field?
Don't you just make a magnetic field?
I mean, that's one way to create an electric field. What's perhaps an easier one?
Make a battery?
I'm looking for something. Actually, batteries, I generally thought of as creating a voltage. And yes, they do create an electric field as a byproduct of that voltage, but only when they go over specific elements in the circuit when the voltage drops or rises.
So create a potential difference somehow?
Yes. All right. Then I'm glad I'm going to go over Maxwell's equations with you guys. So the fundamental way to create an electric field is to create a charge imbalance. So you want to develop more negative charges than positive charges in a particular location, or vice versa. That is the canonical way to make an electric field. And how do you do that? The most common way is like this. Ooh, I can feel my almost non-existent beard standing up. This is called triboelectricity, which a good chance I'm mispronouncing that. And I'm about to misspell it. Many dissimilar surfaces will create an electric field when you rub one against the other. So for those of you with small kids or who are childlike at heart, the plastic slides in a playground and the blue jeans you're wearing will create a charge difference as you slide down the playground slide. You're going to come off of it with a slight charge, and you're going to give the slide itself a slight charge. Other examples, if you are wearing wool socks and you shuffle across the carpet towards an unsuspecting victim, then you reach out and touch them, they're going to get a shock. If you have seen a demo of this in class, and I know that back in the old days you would have done a lab on this in 240, the classic examples would be a Teflon rod and the fur of some unfortunate animal, be it cat or rabbit. Rubbing cat fur against the Teflon rod will make a net negative charge appear on the Teflon rod and a net positive charge appear on the cat fur. Likewise, saran wrap and a glass rod will strip electrons away from the glass rod and leave the saran wrap with overall negative charge and the glass rod with an overall positive charge. So that is the effect of Trebel electricity. This is how you generally generate a charge imbalance. The problem with a charge imbalance is that positive charges are attracted to negative charges. Negative charges are attracted to positive charges. And in general, when you do create a charge imbalance in one location, negative charges are going to find a way to make their way to positive charges, and positive charges are going to find their way to make their way to negative charges. And so charge imbalances don't last long in general. Look forward to me saying a lot on Tuesday. When it's humid, this effect is particularly pronounced, which is why electrostatic demos are difficult to do in the Bay. As Cal's lecture demo person, I'm fully aware that even having a class of students filling up the lecture chamber will screw up electrostatics equipment. Y'all are a bunch of mouth breathers, no offense. You inhale, then you exhale from your mouth, adding humidity to the air. I set up an electrostatics demo that works amazingly well in the absence of students. After 30 minutes of students breathing in the room, doesn't work at all. So let me remind you of a couple of situations where you do generate an electrostatic difference. And I'll do this by means of showing you a demo, and I'll also check the chat window while I'm over there. A charged object in space. Thank you. Thank you so much. That is great. That is what I think of as the right answer. Okay. It is relevant that the balls are insulators because what being an insulator means is that charges are not free to move around on the surface. So if you have an insulator and you want to charge it, you have to rub all around the insulator. The other hand, if you're charging a conductor, the charges are free to move around the surface, and you only have to add the charge to one spot and they'll spread out evenly. Okay, that's how you create an electric field. There's one more way to do it. We'll get to that before the end of class, but this is the main way you create an electric field. And I'm going to refer to this a lot throughout the course of this class, just because I'm going to work in ways to refer to it, because it's something I want you to know. If you walk away from an E&M course without knowing that, then there's stuff you haven't learned, and I want you to learn it if you haven't yet. So I'm hoping there's some people who are still brave. How do you create a magnetic field?
Electrical charge?
Well, what kind of object do you usually think of as creating a magnetic field? What object is it you're analyzing when you get U naught I over 2 pi r?
A magnet.
A wire. A wire. Straight wires, solenoids, toroids. That was your bread and butter problems when you took E&M. And what all of them had in common is they had currents inside of them. Currents are moving charges. The easiest way to create a magnetic field is to move charges at a constant velocity. There's one other way to do it. We'll get to that before the end of class too. Now I'm going to use both capital letters and exclamation points to drive this home. The way to create a magnetic field is to move charges at a constant velocity. This does not require more positive charges than negative charges. We are used to thinking of current as being negative charges. And indeed, this is not wrong. The thing is that electrons mass 9.11 times 10 to the negative 31 kilograms, and protons mass, I don't remember, I'm going to say 2.8 times 10 to the negative 27 kilograms. So there's a difference of 5-ish orders of magnitude in between the mass of an electron and the mass of a proton. When you put a voltage across a wire, perfectly correct, you are creating an electric field. Electric fields push on charges, but which charges move? The electron has a teeny tiny mass. So does the proton, but it's 10,000 times heavier than the electron. So it's the electrons that end up moving. But inside of a current carrying wire, it would be extremely unusual for there to be more positive charges than negative charges. You could do that, although I don't know why you'd want to. But in general, wires that carry current are neutral from the point of view of having more positive charges than negative charges, or vice versa. This makes sense because this is another thing I'm going to find a way to mention again and again and again, because if you don't know, you ought to know. Any questions over the answer to either question 1 or question 2?
Can you just move over slightly so I can see the whiteboard?
Oh, yes. Pardon me.
Thank you.
Great. And because I have demos or videos for everything, no, do not end meetings. Let's look at a quick video with annoying music.
Potential energy to the particles that
An electric current, the negatively charged wires
that
flow
are
through the positively charged wires.
metal connections.
They're not more positive charges than negative charges. That's not how this works. It's just the negative charges are moving far more than the positive charges, but they're both present. Final question. This is the one that's new to this course, so I don't really expect anybody to have the answer to it. But if anybody feels particularly brave, or just like you want to talk, anybody want to take a stab at what the answer is? How do you create light?
Do you excite an electron?
Yes, but can you be more specific?
Sending some type of like energy in the form of like a wavelength to an electron so that it moves up a step.
Sure, that's basic chemistry. Electrons emit light when they fall down through orbitals. I'm on board. But there is a more general rule we can write down. And it is this. Light is created when charges accelerate. Or another way to think about it, this is when they're shook. So all kinds of objects generate light. And in general, they're generating light because they are warm. And this is because inside of warm things, stuff is going like this all the time. This is your basic thermodynamics. If something's going like this, and it has charged particles inside of it, it's making light. The Earth is making some amount of microwave light and some amount of infrared light because the Earth is warmish. You are warmer than the Earth. You are making mainly infrared light. The sun's outer surface is pretty warm. 7,000 Kelvin, 6,000 Kelvin, I don't remember. But it's hot enough that it's glowing and it's creating visible light, which is more energetic than either microwave light or infrared light. This is the greenhouse effect. The Earth's atmosphere is really good at blocking infrared light, but not so good at blocking visible light, thank goodness, or else we wouldn't see anything with the ways our eyes have evolved. So visible light shrieks through, hits the Earth, warms it up. The Earth and stuff on the Earth re-emits infrared light, But that infrared light hits a mirror in the atmosphere because the atmosphere doesn't let infrared light pass through it, and it just bounces right back down. So the visible light comes right through, the infrared light is trapped in with us. The more greenhouse gases we pump into the atmosphere, the more infrared light we have trapped. So, 3 important concepts about how you create electric fields, magnetic fields, and how you create light. You create an electric field by causing a charge imbalance, plus one other way I'll get to today. You create a magnetic field by moving charges at a constant velocity, which does not require there to be more negative charges than positive charges or positive charges than negative charges. And you create light by accelerating positive charges. Again, there doesn't need to be a charge imbalance. You just have to be taking things that are charged and shaking them, which normal heat will do. We haven't gotten there yet in this class, but I'm guessing a whole bunch of you have taken chemistry. This is also the reason why atoms glow when the electrons get knocked up to some other shell and then they fall back down. When they fall back down, they're essentially accelerating. Most of the methods of creating light have to do with charges being accelerated. There is one other way to create light, and I'm not getting into it in this class. I'm not getting it into the end of class, so I'll just tell you what it is right now. You can also create light by physically destroying matter. E equals mc squared. If you physically destroy some matter, then you're going to create light. Quite a bit of light as it happens. From a certain point of view, this happens all the time because the center of stars, which are not, by the way, at 7,000 Kelvin, they're at like 15 million Kelvin. They're destroying matter all the time and creating super energy light. On the other hand, on Earth, we hardly ever do this. We got nuclear power plants, fusion weapons, fission weapons, and that's it. Those are the only 3 times that humans destroy matter that I'm aware of. So, not so much here, but every star in the universe that's officially a star is destroying matter all the time. When they're done destroying matter, they literally don't count as stars anymore. So, it's pretty integral to their identity as a star. Any questions over one of these 3 ideas? And I just want to emphasize, if you walk away from this class with 3 ideas in your head, only 3, I'd like it to be these 3. Because if they aren't these 3, you don't have a good basis for understanding what electromagnetism really is. When I ask for questions, you'll see me do that again and again and again because there's educational research that indicates that people that are going to ask questions usually ask questions within 5 seconds. So I'm going to erase this and move on to something equally old. Oh, great. Hold on for a second. My kids knocked my notes out of order and I reordered them all. And then I put them in some random dumb place because everything here is a blank sheet of paper. So give me a second and let me find them again from wherever it was I put them. All right, I'd like to reemphasize this point. This is fantastic. Fortunately, the notes for the first few sessions are rewritten because I wanted them to be clear. So I've got this pile of old notes I can go off of. This makes it even more likely I'm gonna make a mistake because I remember fixing a bunch of things when I rewrote the notes. So pay extra special attention. It'll be fun to catch me saying something wrong because these notes are out of date. But it's what I'm going to use. What equation is that?
Is that Maxwell's equation?
It's one of Maxwell's equations, usually written as the first one.
Oh, is it Gauss's law?
It is Gauss's law. I'm going to summon the spirit of Aaron here to kick everybody's butt. I assume that you all took Physics 240 from Dr. Quayle. Okay. So this is the version of Gauss's law I'm most familiar with. The divergence of E is equal to the electric density divided by epsilon naught. And you do a volume integral and you use some mathematical theorem, which I think is Stokes' theorem, but it's not written down here, so I really don't know. Then you get a big spill of coffee is what you get. The surface integral of E dotted into dA is equal to Q enclosed over epsilon naught. All right. And the types of problems you did with this were typically finding electric field, of spheres, cylinders, and planes. And the reason you did these three types of problems is that it's way too hard to do anything else with it. So I'm imagining you restricted yourself to just those. But whatever, you do some math, you get what the electric field is. There's all kinds of classical problems where, like, this has a certain interior charge density and you integrate out to a area inside of the sphere, and then you integrate out to an area outside the sphere, but there hasn't been any charge from here to here, so on and so forth. These are like the classic E&M problems. We're not going to revisit these. You're not going to have to redo any of this stuff in this class, but I want you to remember what it means. Oh, these are the wrong notes. This is the notes from a different class. Great. So let's talk about the implications of Gauss's law whilst I search for the correct notes. Ah, here we go. So this first demo has to do with how charges arrange themselves on conductors. So think to yourself for a minute. How do charges rearrange themselves on conductors? And watch this demo whilst I Search for the right notes. So conductors allow electrons and protons to move easily around the outside. Because they want to get as far away from like charges as possible, when a metal sphere is charged, the charges always reside directly on the outside of any conductor, which is why I didn't get any kind of a charge when I touched the little metal ball to the inside of that. Let's look at an alternate, perhaps more convincing example of this. I've got pith balls on the outside and pith balls on the inside. Gonna charge up my big metal sphere. The pith balls on the outside respond strongly to an external charge source. The pith balls on the inside don't feel a single thing. And then just for fun's sake, you can get something similar. In this case, this spark of electricity is in fact happening. Oh, no, it isn't. This is a Tesla coil, not a Van de Graaff generator. So there is no charge imbalance in this, presumably. So you can be shielded from current in the same kind of way that when you are putting charges on a conductor, the charges will collect at the outside. This is why when you're in a car and the car is hit by lightning, stay inside the car. Or if there's someone outside you don't like, trick them into touching it. Because lightning really is a charge imbalance. When lightning streaks out of the sky, there are more negatives than positives in that bolt of lightning, or alternately, rarely more positives than negatives. And so your car has become charged, but it's also a conductor. So the charges are all clinging to the outside surface of your car. You need to wait for the moisture in the atmosphere to neutralize the outside charge before you make any kind of electrical contact with it. And opening the door, putting your foot on the ground counts as making electrical contact. You don't want that shock going from your torso into your foot. That's the kind of way that people lose feet. So that's about everything I want you to remember about Gauss's law, excepting for this. This is called a divergence. And so what we're measuring about the electric field is physically this. how much of it is going out, or how much of it is going in. If the electric field was arranged in a way where there's as much going out as going in, for example, like that, then there is no net divergence. The divergence of E is equal to 0, which makes some sense because the charge enclosed is equal to 0. So of course del dot E is 0. That's what a
Professor,
divergence physically means. And that's almost the only thing I want you to understand about Gauss's law, with the exception that I also expect you to know that for a conductor, charge resides on the outside of a conductor. An insulator can be charged throughout because charges aren't free to move around on an insulator. And that's about it. I can see that there's a chat. Lots of chats. But I can't see the chats. Oh. I don't see anything here that's too relevant, so I'm just going to go back to teaching. May I erase?
yeah.
Great, then I'm doing so. Other stuff I really want you to remember from, I'm going to say last semester, although who knows how long it's been since you took it. Electric fields are a vector. Electric potential is a scalar. The way that I remember this is that electric potential is in some sense analogous to real energy. And electric fields are in some sense analogous to real forces. And the way in which they are analogous is that you take a test charge, put it in a place, and then that test charge will either have a certain amount of energy relative to the voltage, or will have a certain force applied to it relative to the electric field at that point. So V is equal to KQ over R. Nobody here learned E and M using Gaussian units, right? All right. That's only a weird astronomy thing. So I'm guessing this is how you're taught. Voltage is KQ over R, just a scalar. Doesn't matter what the directionality is, because voltage is like a hill. The equipotential points are like lines of constant elevation. You just know what your elevation is. You don't know where you are relative to the center of the hill or any place else. Electric field, however, is generated by taking a derivative with I hat, j hat, and k hat attached to each of the derivative terms, or alternately with x hat, y hat, and z hat, if your teacher was into that instead. And so it does have a unit vector associated with it. It does have a directionality. Potential energy is derived from voltage just by adding that test charge. U equals Q2 times V. And force is recovered from electric field, again, by adding a test charge. Force is equal to Q2 times E. Oh, by the way, I'm sorry. This is my notation for a vector. I put a little squiggly line beneath it. You want to blame anybody? Blame the English. I had a professor who was English, and he taught me vector algebra and differential equations. And by the time he was done with me, it was just set in my head for forever. All right, let's do a test of understanding. May I erase?
I'm done.
All right, in case y'all haven't caught on, I am in no kind of hurry. I'd really much rather beat the topics that we are going through to pieces until they're completely understood than I would rather finish the course. However, that being said, I'm pretty sure we're going to finish the course. All right, no units here. I don't care if these are coulombs or Wonka bars or whatever, as long as you understand that this is some measure of charge. And the X's are always midpoint, even if they don't seem to be, because I am a bad drawer. So is the E field here in the midpoint high, low, or zero? Remember, electric fields are always pointing from the negative to the positive. Thank you, Ben Franklin. Oh, wait, vice versa. They're always pointing from the positive to the negative. Thank you, Ben Franklin. Here we have Q equals 3, Q equals 3, so identical charges on either side. And then what's the V field here? Q equals 3, Q equals negative 3. Is it high or low? In other words, is it 0, high, low? And what's the V field here, where Q equals 3 and Q equals 3? This is a situation where I very badly want to send you into breakout rooms. I'm going to set the timer on my phone for 2 minutes so you can think about it. And I'm going to look for breakout rooms. Again. Okay. Anybody feel particularly socially bold who wants to share? That's fine. Electric fields represent the paths that particles will take. So if you're in my E&M class, we have to draw electric field after electric field after electric field because that's how I roll. Here we're just going to draw a few. Given that the electric field always follows the path a positive charge would take if it were released at the beginning point, if I release a positive charge here, it's going to go like this. If I release one here, it would flee this Q equals 3. And then as it gets further away, it will be drawn more and more and more to the Q equals -3, so on and so forth. Point being, at this spot, there is a strong electric field. I'm going to call it positive because it's pointing to the right, and I'm used to things pointing to the right being positive. Note that because of Ben Franklin, we pretend both that positive charges move inside of circuits, which we've already covered is not true. The negative charges do most of the moving. And also we draw electric fields as if the positive charges are the thing that's moving. And again, it's usually negative charges because they're super light. You know what they say about Ben Franklin? That guy was a dummy. They didn't really say that about him. He was a genius. In this case, if I release a charge here, it's going to flee Q equals 3 as quickly as possible. And then it's going to get over here and it's going to say, hey, I don't want to go there either. So forget about it. I'm going this way. Bye. So the electric field here is 0. As far as voltage goes, let's say this is 10 volts. Oh, I didn't mark the location of the charge. Let's say this is negative 10 volts. Cool, whatever. Out here, maybe we're at 5 volts. The way that you determine the shape of the voltage field is you draw the E fields, and the E fields are always perpendicular to the voltage field, or at least that's how I do it. Positive 5 volts, and right here in the middle, 0 volts. So net voltage, 0. Let's say it's 10 volts. This is also at 10 volts. Maybe this is 8 volts. Right here in the middle, maybe this is 5 volts. Remember, voltage is very much like a hill. So the analog to this situation would be this. There is a valley in between, but it's not at 0. The analog to this situation would be this. Because this is a negative voltage and this is a positive voltage. Right here, 0 volts. All right. We're far from done with the E&M review, but this is stuff I expect you guys to know. Like, it's fair game for the class. Not asking you to derive the electric field of a sphere, but asking you to understand what electric fields and electric potential really are. Any questions before we move on? All right. I am erasing. Whew. All right. I'm not going to bother with this example because it's just basic kinematics. Anybody want to see a basic kinematics problem applied to E&M? I mean, you can say yes. So the typical way you create a north and a south pole is you take something that's magnetically charged and you drag it over metal, and that imparts, not magnetically charged. You take something that's magnetic and you drag it over metal, and then the domains in the metal realign themselves, and now that thing is also magnetically charged. Not every metal, but iron, cobalt, nickel, neodymium, some other ones I'm not remembering because I just don't remember them. Those metals. The reason that these metals are able to be magnetically charged is that their outer electron shell, their valence shell, for those of you taking chemistry, has a property that there's an electron that's unpaired in a way that it can align itself and create a current loop. So a straight wire creates a magnetic field like this. A wire that's bent into a curve creates a magnetic field like this. And as it so happens, if you try to isolate a magnetic field, chomp, say it's a bar magnet, all you do is create a new north and a south pole. Because the thing that fundamentally generates magnetic fields is these little current loops, there's no way to isolate it. Anytime you have a little current loop, it's going to generate both a north and a south pole. Because you can't separate the north from the south, that means there's no divergence. Whatever surface it is I draw, here's a north and here's a south, I'm going to be clever and put my surface area around that. And the divergence is 0. There's as much going in as there is coming out. AKA, there are no magnetic monopoles. I want to be extra clever. I'm going to chop this thing in half. Yeah. And then I'm going to put a new Gaussian surface around that. But the joke was on me. Because as soon as I try to isolate this, there's a new South Pole, North Pole combination. And when I try to slam the Gaussian surface around that, I get the same thing. There's as many field lines going in as coming out. So this is Maxwell's second equation. Often overlooked because it's boring. This is the equation that says there are no magnetic monopoles. Doesn't make sense. Does anybody have any questions over it? All right. Video break. This is not the perfect time for this video, but the perfect time for this video doesn't exist. Get ready to have your conceptions of how the universe works challenged whilst I grab some paper towels and sop up this coffee stain so that I'm not walking in fresh coffee anymore.
Only a few elements can be permanent magnets. Iron is one. Copper is not. But if you pass an electric current through any metal, it becomes a magnet. An electromagnet. But how does this work? Well, strangely enough, it's a consequence of special relativity.
Special relativity is the fact that in our universe, length and time aren't absolute. They're perceived differently by observers moving relative to each other, hence relativity. For example, if you measure carefully enough, you'll find that time passes slower for observers moving relative to you. Hey Derek, when did you last shave?
6 hours ago. Actually, it was 5 hours, 59 minutes, and 59.99999999999.
And moving objects are also contracted in their direction of motion.
You're looking slim, only in your frame of reference. So when an object is moving relative to you, it actually takes up less space than when it's not moving. And even though this effect is obviously way tinier than we've shown, length contraction is what makes an electromagnet work. Picture a copper wire. It consists of positive metal ions swimming in a sea of free negative electrons. Now, the number of protons is equal to the number of negative electrons, so overall the wire is neutral. So if there were a positively charged cat nearby, it would experience no force from the wire at all. And even if there were a current in the wire, the electrons would just be drifting in one direction, but the density of positive and negative charges would still be the same, and so the wire would be neutral, so no force on the kitty. But what if the cat starts moving? Imagine, for simplicity, that the cat is moving in the same direction as the electrons with the same velocity. Well, now, in my frame of reference, the wire is still neutral, and so there should be no force on the cat. But consider the same situation in her frame of reference.
In the cat's frame of reference, the positive charges in the wire are moving, so according to special relativity, their separation will be ever so slightly contracted. Also, from this perspective, the electrons aren't moving, so they'll be more spread out than before. Remember, objects take up more space when they're not moving than when they are. These two changes together mean there's a higher density of positive charges in the wire, so it's no longer neutral, it's positively charged, which means that the positively charged cat will feel a repulsive electric force from the wire.
But in my frame of reference, this seems mysterious. There's no force on a stationary charged cat, but a moving cat is somehow repelled from this neutral wire. How do you account for that force? Well, we say it is the magnetic force. And that's mainly because a wire with current in it deflects nearby magnets. So really what this experiment shows is that a magnetic field is just an electric field viewed from a different frame of reference. In the cat's frame of reference, it is repelled from the wire due to the electric field created by the excess positive charges produced by the effects of length contraction. In my frame of reference, the cat is repelled from a neutral wire due to the magnetic field created by the current flowing in the wire. So whether you see it as an electric or a magnetic field just depends on your frame of reference, but in either case, the results are the same. So an electromagnet is an everyday example of special relativity in action. Now that might seem crazy since electrons drift through wires at about 0.00000000001% the speed of light. So how can special relativity have anything to do with it? Well, the truth is there are enough electrons in a wire, and the electric interaction is so amazingly strong that even the minuscule effects of length contraction can produce significant charge imbalances that produce a noticeable force.
So special relativity explains electromagnets. But what about permanent magnets?
Yeah, I mean, there can't be electrical currents flowing around inside lumps of rock, can there? Click here to go to Minute Physics, where we'll explore magnetite, compasses, and all the wizardry of permanent magnets.
So I was just talking about that. All right, well, I'm looking ahead at my notes and I can't imagine what I'm going to do in 5 minutes. So I'm going to give everybody a 5-minute break. I'm setting a timer on my phone. Come back here and meet me for the lab in 5 minutes. So grab a snack, do whatever you got to do. I'll see you in 5 minutes. And we're back. So I thought I was going to get further this class, but slow and steady is how I like to teach. So I'm perfectly happy to get as far as we get. On Tuesday, just so you're forewarned, I will run late. And I'm going to leave the recording on until I finish the preamble for this lab. Then I'm going to turn it off. And I'm also going to kill the video because this is a fixed camera and I don't really see any point in looking at the whiteboard for the entirety of the lab. Hit me up on chat. I'll be paying attention to it when you have questions about the lab. But before we dive into the lab, there's something I need to go over that I haven't gone over yet. I said there was another way to create an electric field, another way to create a magnetic field. This is a province of E&M, but it's also the province of this class, especially because there's one Maxwell's equation you haven't learned yet. Changing electric field creates a magnetic field. Changing magnetic field creates an electric field. Looks like this. Magnetic fields in red, electric fields in blue. The electric field's changing, creates a new magnetic field around it. The magnetic field's changing, creates a new electric field around it. In this context, changing can mean changing direction, or intensity, either because the thing that's generating it is generating more or less, or because you're moving it closer or further. Let me show you at least one example of how this works. I think I only have one relevant video, but I'll check. By the way, the canonical example you saw of this, while you took E&M, you'd better have seen this, is this problem. Slide this rod over to the side, or slide this rod inwards, and that counts as changing the magnetic field. What you're really doing is changing the magnetic flux, which is the important thing here, but more about that on Thursday. And so you should have learned mathematically solid how to calculate what the induced current, the voltage / E field that's created, is when you slide this rod and change the magnetic field. That's the problem you did last semester about this kind of stuff. Probably also did another couple of problems but this is the one that everybody does. So I'm sure Aaron put you through it. Now let me show you some examples of how this works, or at least one example. I don't think I have the rest of them uploaded. Hopefully by next week. So here's 7 electromagnets. I'm going to run current around them, and they're going to create strong magnetic fields pointing up, because you run a current around something in a circle, magnetize a bar, magnetic field points north-south going up and down. This thing is being supplied with AC current, so the magnetic field is switching up and down, up and down, up and down 60 times a second. That means that I'm creating 7 different current loops inside of that aluminum dish. Aluminum itself cannot become permanently magnetized, so it's the changing current inside of it that is responsible for that levitation. As you recall from E&M, or if you don't recall, you'll recall it now, there's something called Lenz's law. It says that when a field is changed, a new field will be generated in such a way as to fight the change. So as the magnetic field is flipping north-south, 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 so too are the current loops changing direction such that there's a net repulsive force and the dish stays where it is. The changing magnetic field creates an electric field. In this case, 7 different electric fields, all of which are driving a current. That current is creating a magnetic field. The magnetic field is opposing the magnetic field of the electromagnet beneath it. By the way, if you carefully work this out using Lorentz law, you'll find out that this has to be shaped like a dish to work. If you try it with a flat piece of metal, the forces don't cancel out in such a way as to give you an upward motion. When I force the metal dish very close to the electromagnets, I'm making the current much, much stronger. That means I'm making the dish much, much hotter, because when current flows through something, heats it up. By the way, GE gave us the specs for this under a licensing agreement where we were supposed to put GE on the outside of it, and we never bothered doing that. So nobody tattle on us, please. Yep, those are, I guess, all the demos I have uploaded that are relevant. That is too bad. Let me check this real quick. Oh, this is also relevant. So I've got a big old coil of wire with a solid metal cord running through it, just to amplify the strength of the magnetic field. When I run current through the wire, that's going to create a magnetic field. And when I put a ring around on the top, that's going to cause current to flow through that ring. AKA, all of a sudden, that ring is going to be generating a magnetic field. And that magnetic field is going to be opposite in direction from the magnetic field that created it. Ah, quit it. That didn't give us much because it was supplied with a DC voltage. So the magnetic field changed once and then it remained constant. So it created a current loop when it went from off to on, and then that current loop faded away. Watch what happens when we energize the coil with alternating current instead. Sure, whatever. You cut a hole in the ring, it's not a complete circuit. So current can't flow, no lift. So that's DC again, only now the the disc of metal is supercooled. Lowering temperature makes it so the electrons can flow more freely, so we get more of a kick out of it because the current was bigger. Ah, quit it. All right, on to the lab. Once I finish explaining the lab, I'm going to turn the recording off. Apologize for that. That was an astronaut chatting with you about stuff. Now is not the time. Here we go. Got it. So this lab is going to be done entirely through the use of this applet, which is HTML5, so it should work on pretty much all your computers. If it doesn't work in Chrome or whatever, I advise just immediately going to Firefox, but I'm loading this in Chrome without any trouble. I just find that in general, Firefox works better for almost everything. So there's a magnet. There's a compass. Cool. Here's a magnet with a coil that can be used to power a light bulb. Here's an electromagnet that can create a magnetic field. Does not require a permanent magnet, does not require any kind of a cord. Here is a transformer in which there's many loops here and only a couple loops here. And here's a generator on a wheel. How do I change the number of revolutions per minute? Oh, I have to turn the water on. Right. And so you have various things that you can explore. And here is the actual lab. So you click on Lab 1, Faraday's Electromagnetic Lab, download the PDF, and voila. What I would like you to do is write this up by hand, ideally working in groups. If you guys want to chat each other and share your Gmail contacts and stuff like that, then I think it would be much more useful to be actually chatting with somebody as you go through this. I think the lab is pretty self-explanatory. If you have access to a printer, you can print this out and fill in the fields where there's blank space. But realistically, probably most of you are going to be just doing this on a sheet of paper. So just write for me, fire magnet tab, left tab, make it obvious for me which questions you're answering. And that's what you're going to upload as your completed experiment. Are there any questions? 5, 4.
When does this due?
I'm going to set that right now. I'm going to say, well, you should complete it tonight, for one thing. I'm going to make it due next Tuesday at midnight in case somebody has a job requirement that requires them to go, or you have some other pressing matter that for some other class that requires dealing with. You do not have to complete this tonight. And this way you'll have a week to inspect it, and you'll get an opportunity to talk to me if anything really trips you up and you're not staying here tonight to ask me questions in person.
Okay, thank you. And I had another question about the mastering physics.
Yeah.
Did you want us is there any work due on Friday? I had to figure that out. And I might not be able to get it done by Friday, so I was just wondering about that. Or get like signed.
Friday. I'll go back and I'll review the mastering physics due dates. Given how far I got today, I think I'm going to be working on chapter 31, or you're going to be working on chapter 31 until about next Tuesday. If that's the case, then I'll make the homework due the Tuesday afterwards.
Okay, thank you.
So let's not do this Friday. And I'll talk more about homework and due dates and expectations and stuff like that on Thursday. But it's not due on Friday as a bottom line. Nothing's due this week.
Okay, thank you.
Any other questions? Then I am going to stop recording. I see that there's people inviting each other to Discord channels. That works too. Can G-chat. I'm going to turn the video off because I'm guessing that nobody really wants to stare at that whiteboard the entire time. And I'm going to turn mute on because I don't think anybody wants to listen to the sound of me chewing. But nonetheless, I will be here. If you have questions for me, either turn your mic on and say something or leave me a message in the chat screen. And unless I'm briefly out of the room, I'll be back with you shortly. When you finish with the lab, I'd like to ask you to log off. That would be my signal that everybody is done with the lab and I can proceed with my life. All right, that's it.